Music is something integral to our being because it's been with us for so long. Mozart, Beethoven, Bach, Elvis Presley are famous musicians of the past, but music has definitely been around for much longer. For example, this thing is a flute made from animal bones. Using radiocarbon dating, archaeologists have established the age of this flute to around 40,000 years ago. To put this into perspective, we were making arts and crafts depicting woolly mammoths starting around 35,000 years ago. Over our long acquaintance with music, we have had lots of time to ponder what kinds of music to make, and what to make music with. Instruments people have used include, but are not limited to, their mouths, drums, string instruments, and, like our ancestors from 40,000 years ago, wind instruments. One important thing to note, however, is the variations in these instruments. Why does the violin sound the way it does? Why doesn't a trumpet do the same thing? Although instrument makers are and have been familiar with the effects different materials have on instruments, comparatively few people who appreciate music truly understand how we make the sounds which come together to form music. This, I believe, is due to the belief that taking an empirical approach to the creation of music is tantamount to butchering the emotional aspects of enjoying it, much like an English class butchers a book by overanalyzing. This video aims to show that this is not true. Knowing the way that the instrument's physical properties play a role in creating a certain sound will enhance your experience with music. First off, we can start with the most fundamental aspect of making sound by asking the question, what is sound? Chances are that someone has mentioned it to you at some point in the past. Sound is just vibrations. That is the simplest way to put it. Sound is just vibrations. But if we look a little deeper, this doesn't make much sense. If we're listening to another person playing an instrument, say in a concert hall, you're nowhere near the players, yet you still hear these so-called vibrations. How are these vibrations getting from the instruments into your ear? How are you detecting them? The answer is very simple. The air is vibrating, transmitting sound to your ears, and you pick it up. But at a fundamental level, the air isn't actually vibrating. But the instruments that vibrates will cause compression waves to move through the air. This is what the cochlea in your ear pick up, and that's what sound is. Here's a good visualization of this phenomenon of sound waves. The blue dots here represent air particles, and the green sinusoidal wave is the mathematical representation of the sound waves, with compressions at the peak of the sinusoid and rarefactions or reductions in density at the troughs. One continuous note being played is a stream of these sound waves, moving at about 343 meters per second, at a certain frequency. Frequency is described as how many times something is repeated for each unit time, and in this case, our unit of time is seconds. The internationally accepted unit for frequency is hertz, or cycles per second. Greater frequency in this case means more sound waves are reaching your ears every second, which you detect as a higher note. For example, a middle C, denoted as C4, has a frequency of about 261 Hz. A4, on the other hand, has a frequency of 440 Hz. Now that we've covered the most basic question, let's get to the main topic. Why do certain sounds seem different than others? For example, maybe you've been bored before and began tapping your pen onto the desk. If you've done that, you may have noticed that there's a huge difference between pen tapping on a plastic desk and on a hardwood desk. Another more relevant example would be violins versus clarinets. Why does the clarinet usually sound so mellow, and the violin so vibrant? Even if we removed all variables except for the instruments themselves, You can imagine that even when playing the same note, there is clearly a difference. So what actually makes them sound different? Here's what: the instrument. More specifically, the materials in the instrument, as well as the way the sound is created by the instrument. Remember, the thing that's actually making the sound waves is the vibration of the instrument. This is done in several different ways. Let's take a look at the violin first. Here's a clip of the violin played in slow motion. As you can see, the string is moving around pretty violently as the bow moves. This is the source of the vibration, but it wouldn't be loud enough to reach our ears without some help. Remember that the strings are actually pretty strongly bound to the violin. This makes it easy for most of the vibration from the strings to be channeled down the bridge into the body of the violin. Then, the body vibrates, causing the air around it to be disturbed, finally creating sound. Other similar instruments, such as the viola or cello, or even the Baroque variation of the violin, really only differ in terms of size and some adjustments to the fingerboard and other parts of the instrument. These changes result in quite different sounding instruments, but the main principle is the same. Clarinets, as you may imagine, make sound in a very different way. The clarinet is a closed pipe, which is simply a pipe that is closed on one end. The closed end is where the clarinet player blows into the instrument. It's not actually closed, but for the sake of sound propagation, we can say it is. The reed on the clarinet vibrates when the player blows into the clarinet, which causes the mouth of the clarinet to become blocked and unblocked very rapidly. This causes pressure waves to be formed in the clarinet, which are differences in pressure rather than differences in air particle compression that we see in sound waves. As the pressure waves travel down the air column out the other end of the clarinet, some of the waves bounce back up to the reed end, creating a standing wave, which are waves of specific frequencies that remain stationary inside a hollow object. The standing wave is perpetuated by continually blowing into the clarinet, and this standing pressure wave causes the air at the bell end of the clarinet to make sound waves. Just to make this segment a little shorter and less boring, a trumpet basically makes sound in the same way as a clarinet, except instead of a reed vibrating, the player's mouth is what causes the pressure waves, and also the bell of the trumpet is a much greater contributor to the sound than the bell of a clarinet. Next, we look at the materials used to make the instruments. Violins are made almost entirely of some sort of wood, usually a combination of spruce and maple. In order to see the effects of the wood on the resulting sound of the violin, we need to look closer. Really quite close, in fact. The chemical composition of wood varies from species to species, but it's usually around 50% cellulose by weight. Cellulose is a polysaccharide, or a complex sugar, which is extremely tough. Wood also contains 27% lignins, which are a class of massive complex carbon-based molecules. Both of these contribute to the durability of wood. Cellulose and lignins are both very densely packed in wood, and the resulting resilience allows a small amount of energy of sound waves to be absorbed by the material. This property of wood is especially important in a violin, as the body actually creates the sound, and the way in which the material of the body responds to the vibrations of the strings is key to the specific sound characteristics of a violin. Speaking of strings, the materials of the strings is also important to the sound of a violin. The strings are made of either steel or cattle gut, and due to the strength of both materials, they're both able to withstand the violent vibrations that come with playing the violin. You would not be using butcher's twine as violin strings, since they're made with cellulose fibers which are not flexible enough for the vibrations. Trumpets, like French horns or trombones or tubas, are generally made from brass, a type of metal alloy made with varying proportions of zinc and copper. Sometimes the expensive ones are coated with gold and silver to prevent corrosions and look fancy, but it doesn't contribute to the sound quality of a trumpet. What does contribute to it, however, is the crystalline structure of the brass. This is a model of what a crystal looks like. To be specific, this represents sodium chloride, or table salt, which is very distinctly not brass, but it will do for the purpose of this video. You can see that there is a very obvious pattern in which the sodium and chlorine atoms are arranged. A similarly ordered structure can be seen in a number of different simple solids, such as various salts, pure metals, or even alloys. These crystals are relatively rigid, but different crystals vary in rigidity. For example, gold is actually very malleable. You can hammer a little bit of pure gold into a sheet of gold only a few atoms thick. Meanwhile, steel is not so malleable unless it's extremely hot. Assuming you're able to hit a bar of steel hard enough, at room temperature the steel would snap and break. Otherwise, the steel bar would maintain its shape very well. Regardless, the sound and pressure waves we make using instruments aren't hard enough to bend metal, so the brass of the trumpet tends to reflect the energy of the waves rather than absorb them. This creates the fanfare-like sound quality associated with trumpets and other brass instruments. Now we know why instruments sound the way they do. We just combined a bit of chemistry and a bit of physics together to figure out why and how instruments make different sounds. I hope that now, when you hear the wonderful sound of violins or the powerful blare of a trumpet, you think of the ingenuity that went into the creation, development, and perfection of those instruments. And maybe, if you hear of the latest scientific breakthroughs, you can think of the science that goes into music. Knowing music doesn't destroy music. It just gives people more things to appreciate.